Margaret, how do I set up the iPhone? Hi kids! I'm making this video for you guys because I know you have a big statistical physics exam coming up. And as your grandpa, I've lived a very long life, so I've seen a lot of thermodynamics in my time. I know how much you guys love my stories, so we're going to hear a lot of them in this video, and you can't skip it. You can't. We'll start off our story when I was just a wee lad in the microcanonical ensemble. In this ensemble, we follow a recipe that was carried down through generations in our family. From our microscopic counting, we'll be able to find entropy, from there, temperature, from there, energy, and lastly, we'll be able to find our heat capacity. As I tell you all about thermodynamics, we'll make sure we keep this recipe in mind. First, we'll start our story with the ideal gas, particles that seldom interact with one another. These particles are identical. Each of them has F quadratic degrees of freedom. The excited diatomic has 7 of them. Each particle could contribute 1/2 kT amounts of energy to the group, multiplied by their quadratic degree of freedom, and thus the total thermal energy was described by the equipartition theorem. Now, again, kids, the equipartition theorem only holds if each of the particles that are identical don't interact, and that we're in high temperature. We're going to see thermal energy again in the first law of thermodynamics. If you've heard about the conservation of energy, this is it. The change in the thermal energy is going to be equal to the energy leaving or entering the system. We'll use quantities such as heat and work to define the energy leaving or entering our system. Heat is the spontaneous transfer of energy from a system of low temperature to a system of high temperature. And we'll define work as our non-spontaneous transfer of energy. The most common type of work that we'll see is compression and expansion work. If I compress something, then I'm going to put energy into it. If I let something expand, then I'm taking energy out of the system. I cannot emphasize this enough. Everything that we're talking about here in terms of changing a system is done quasi-statically. Doing things quasi-statically is to do things slowly, and that the changes that we make are reversible. Now kids, remember that we're primarily concerned with the ideal gas for right now, in which the particles don't interact. For this ideal gas, we can do adiabatic compression or expansion, in which we don't allow heat to leave or enter the system, or we could do isothermal compression or expansion, in which we keep the temperature constant. Now, don't forget this important point. Keeping certain thermodynamic properties fixed is really key to understanding different ensembles, which we'll talk more about later. Before we move on from heat and work, I should define something called heat capacity, which is a key step in our recipe. Heat capacity is the amount of energy that we need to put in or out of the system to change its temperature by some amount. For example, water has a relatively high heat capacity of around 4.18. This is why it takes water a fair amount of time to boil, as seen here. Have you ever looked at an object and wondered how much energy is needed to make this system entirely? Well, enthalpy's got you covered. Enthalpy is equivalent to the energy of the system, plus the work needed to compress the atmosphere to make room for our system. Don't worry, enthalpy is more than a thought exercise. It's really important to understanding a lot of chemical reactions that happen under constant pressure. Kids, I promised you counting, and here we are. Now, I want you to consider a system of 2 particles which have 2 possible states. They're either sitting or standing. The single particle state will be the state of each particle, and the microstate will be the connection of all of those single particle states in one snapshot of the system. The macrostate will combine microstates with the same fundamental feature, such as 2 sitting down particles, or 2 standing up, or 1 sitting and 1 standing. The multiplicity is going to be referring to the number of microstates corresponding to a given macrostate. See how these numbers are really easy to calculate? It's definitely going to stay like this for the entire time. Another common two-state system is paramagnetism, in which the spin is either up or down. This two-state system stuff is kind of fun and easy, but what if we were to get a little bit more complicated? Consider an Einstein solid, which is a lattice-like structure in which it's made out of a bunch of one-dimensional harmonic oscillators. The solid will have a certain amount of atoms and a certain amount of total energy units, assuming that it's isolated. These energy units can be dispersed amongst the particles in any arrangement. Given the two-state systems that we had before and this Einstein solid, we can again find the multiplicity by counting. I'm not sure how much time you have on your exam, but I don't think you can do enough counting for 100 particles with 100 energy units. Well, it's a good thing we have formulas to calculate the multiplicity for all these different systems. Before we move on from counting, there's a really important fact that we need to consider, which is the fundamental postulate of StatPhys. This postulate says that all microstates corresponding to a given macrostate have equal probability of occurring. Now, this doesn't mean that every macrostate has an equal probability of occurring. If I have 2 macrostates, one of which has 20 microstates and the other only has 2 microstates, the one with 20 microstates is going to be more probable to happen. Eventually, after a long time, the system will be able to explore all possible microstates. This is called ergodicity. This is why we have to wait a long time to get good statistics. We also see that in the thermodynamic limit, which means as the number of particles gets really, really big and the temperature increases, we'll see that the system goes towards its most probable macrostate. Now here is where we really have to talk about entropy. Entropy is directly related to multiplicity, so if we have a high multiplicity, then we'll have high entropy. Now, if we think back to previously, when we had high multiplicity, we had a really high probability of that macrostate occurring. So the most likely macrostate actually has the highest entropy. This is the second law of thermodynamics, that entropy tends to increase. Also, entropy is an extensive quantity, so it will increase depending on if we have more particles in our system or if our volume gets larger. Now, going back to our ideal gas, which had n non-interacting particles, we'll consider the quantum mechanical problem of the particle in the box. The energy solution for the particle in the box will yield discrete values of energy as it's a bound state. From these discrete energies, we could then find a formula for the multiplicity, and then from there, we could find the entropy for this ideal gas. What we did here is just using our recipe. We created our microscopic model, did some counting to find the multiplicity, finding our entropy. From there, we can find our temperature, energy, and our heat capacity. However, kids, there's a very important concept that we did when we were finding the multiplicity of this ideal gas, which is the notion of indistinguishability. Since all of the particles in an ideal gas are exactly the same, if I switch the labels on these 2 particles, nothing actually changed. So we have to make sure we divide by n factorial, n being the number of particles, to make sure that we account for this, as we only want to count the unique microstates. We talked about states such as the paramagnetism model, the Einstein solid, the ideal gas, in which we found the heat capacity for all of these scenarios using our recipe. But now we want to know, what is the purpose of the heat capacity and where can we go from here? First, we've got to talk about equilibrium. We all love it, we all know it, or do we actually know it? Recall the second law of thermodynamics. Our system wants to go to the state that has the highest entropy, meaning that as the system reaches equilibrium, it will reach this state. Now, there are three types of equilibrium that we'll discuss: thermal, chemical, and mechanical. Thermal equilibrium is when the two systems that are in contact with one another share the same temperature. Mechanical equilibrium means that the two systems have equal pressure, and chemical equilibrium means that the two states have the same chemical potential, which means that the particles don't have a preference towards what system to go to. Most young ones nowadays talk about the first and second laws of thermodynamics, but the third law is still really important. The third law of thermodynamics says that at the ground state, when the temperature approaches 0, the multiplicity will equal 1. And since entropy is related to the natural logarithm of the multiplicity, the entropy will just be equal to 0. And furthermore, the heat capacity will also be equal to 0. This law holds for many systems, so it's important when you're looking at a system to view what happens as the temperature approaches 0 to see if it obeys the third law or not. We'll also see that for systems, in the low temperature regime, the energetics will usually dominate and the system will want to go to the minimum energy. Whereas if we were to increase temperature, the entropy actually drives the system, and the system will want to gain the maximum amount of entropy. Let's get back to heat capacity. Heat capacity is so important because when we're studying phase transitions, we'll actually see that there's a huge spike in the heat capacity. This is because the heat capacity is the amount of heat required to change the temperature of a system. But during a phase transition, there's no temperature change, but there is still heat leaving or entering the system, which is why we see a huge spike in the heat capacity. Thus, we say that heat capacity is a signature of a phase transition. We talked about thermal energy and enthalpy, but there's also other quantities such as the Helmholtz free energy and the Gibbs free energy. These four make up our thermodynamic potentials. These four quantities all have units of energy and they create mapping between different thermodynamic properties. Even though entropy isn't technically a thermodynamic potential because it doesn't have units of energy, it's still our key player in our microcanonical ensemble, in which we have fixed thermal energy of the system, the number of particles, and the volume. From these four thermodynamic potentials, we can develop four thermodynamic identities to see what the potentials are functions of. Since the free energy is a function of N, V, and T, it's going to be the key player of the NVT ensemble, in which the system will try to minimize the free energy. The NVT ensemble is sometimes referred to as the canonical ensemble, and it's very similar to the microcanonical ensemble, except that we hold temperature fixed by connecting the system to a heat bath, so it stays at a constant temperature. Similarly, the Gibbs free energy is a function of N, P, and T, so when these quantities are held fixed in the NPT ensemble, the Gibbs free energy will be minimized by the system. It's important to note, just as we saw with entropy and thermal energy, all of the thermodynamic potentials are extensive quantities, meaning that they scale with the size of the system. All of these different ensembles show once again that the importance of our problems is figuring out what is being held constant to determine what the system does in equilibrium. To find the minimum Gibbs free energy in the NPT ensemble, we're going to have stable states, which are the absolute minimum Gibbs free energy, metastable states, which are local minimums in the Gibbs free energy, and unstable states, which are local maximums. For a given substance, we can plot a phase diagram, which shows how at different pressures, temperatures, or volumes, the system will either be a solid, liquid, or gas, or some sort of combination. Here is an example of a phase diagram for water, H2O. We can see that different sections of the P versus T graph have solid, liquid, and gas states, meaning that these states have the minimum Gibbs free energy and are hence the most stable states. The lines on this graph are coexistence lines. For example, the one between liquid and gas means that for the pressure or temperature on this line, both the liquid and gas states will be stable, and hence they'll both be present at the same time. The point located to the far right is the critical point. Past this point, there's a continuous change between the liquid and gas phases, and there's no discernible difference between the two. Hence, it's just a fluid past this point. The point connecting all three coexistence lines in the center of the graph is called the triple point, and at this point, the gas, liquid, and solid states all coexist. Typically, when we look at phase diagrams for a substance, we'll see that the coexistence lines on a P versus T graph have a positive slope. Yet for water, we can see that the line bridging the solid and the liquid phase actually has a negative slope. This is really unique to water and isn't common between many other substances. This is because when we're on the coexistence line, we expect that at some fixed temperature, as we increase the pressure, we should get a solid form of the substance. But for water, we can see that we actually get the liquid state as the most stable. This is specific to water because whenever water freezes, its volume actually expands, and so when we increase the pressure, we'll actually end up getting the liquid form of water instead of the ice form. Previously, we talked a lot about the ideal gas, in which we don't assume any interactions between the particles. But if we want to properly examine phase boundary behavior, we have to take a look at the interactions between the particles in non-dilute systems. To look at the interaction energy between two molecules, one can consider the van der Waals potential. We can see here that potential is a function of r, in which r is the distance away the molecules are from one another. When r gets very small, we have a repulsive piece, and that arrives from situations such as the Pauli exclusion principle and electrostatic repulsion. We can see that at a good distance away, we get the minimum energy, which is what the system wants to be at. This is the attractive piece. So in order to count for interactions in our ideal gas law, we need to make sure that we include the repulsive piece and the attractive piece. Each molecule in our volume will take up some amount of space. In addition to that, the molecule that is attracted to it can't be too close to the other atom. It can only surround it. This will be our repulsive piece that we'll include into our ideal gas law. For the attraction piece, we're going to use an approximation called mean field theory. The mean field approximation is very simple. If I'm in some sort of range away from the molecule, I'll have some sort of energy associated with it, which is attraction. But if I leave that range, then I'll have no energy. We'll keep note of this approximation as it's not perfect and might cause some issues for us down the road. After incorporating these two key ideas into our ideal gas law, we arrive at the van der Waals equation of states. Now that we have this new equation of state, and we can develop an equation for the Gibbs free energy as a function of volume using our thermodynamic identity, we can develop graphs that connect P, V, and G and see how they look for different values of temperature. What we see here is how pressure varies with volume using our new van der Waals equation of state. We can see that there's a portion for the low temperature isotherms in which the change in pressure over the change of volume, which is the slope in this graph, is greater than 0. One part of mechanical stability is that the derivative of the pressure with respect to volume must be less than or equal to 0. This makes sense intuitively, as if I were to decrease the volume, I should get an increase in pressure and vice versa. If we consider this low temperature limit looking at the Gibbs free energy, we can see this loop that appears at the top, which is called a van der Waal loop, and it is the same phenomenon that we saw previously in which we didn't have mechanical stability. It is a direct result of using that mean field approximation. Since the system will always go towards the most stable Gibbs free energy, which is the most minimum Gibbs free energy, the states labeled by 3, 4, and 5 will actually never be expressed in the system. So if these points aren't actually expressed, then what's going on between the transition from point 2 to point 6? Well, you might have guessed, we have a phase transition occurring here. Now, we know that we should have some sort of line connecting point 2 and point 6, but how are we going to figure out what this line is on our P versus V graph? Asking where this phase transition occurs is also asking at what pressure value in this P versus V graph does the phase transition occur. And we can find this using equal area Maxwell construction. Using Maxwell construction, we can find two regions that have equal area, and then we can separate them by a line, which we'll call a tie line. This is where the phase transition occurs. Next, we can recreate our P versus V graphs and replace those regions by the tie lines to give an accurate representation of actually what's going on. The result for a few temperatures looks something like this, in which we can see the tie lines are implemented. The region in which the tie lines are represented is called the coexistence region. The point located at the very top of the coexistence region is the critical point. Relating this back to the critical point we talked about earlier, beyond the critical point, there are no discernible changes between liquid and gas, which is what we see here. Beyond this critical point, we don't see any more tie lines, and we are officially out of the coexistence region. Well, that was a lot of information. What are some of the key takeaways that I want you kids to learn so you know what to expect walking into your exam tomorrow? One of the key concepts to take away is how we went from microscopic models and we arrived at macroscopic solutions just by using our recipes for different ensembles. We also expressed the many ways to connect different thermodynamic variables. And at times it may seem like a lot, but we also need to consider what are we holding constant in our system and what do we want to know more about. That's it for now, kids. Have a good exam and happy holidays from me and your grandma.